Okay, I got a few emails and questions in class yesterday about some of your homework, in particular the first homework set, problems 12 through 14, on center of mass, moment of inertia, things like that. And in particular, the problems that had random letters like constants A and K as opposed to numerical values. As I pointed out in class, that's because there's really two ways to solve a problem. One is for me to give you a specific problem, find the volume of a cone if the height is 10 and the radius is 4. Plug into formula, done. Mathematically, we prefer it if we found a general formula for all cones. So we say find the volume of a cone if the height is h and the radius is r. Nothing changes in the setup except that instead of having constants that are numerical and like 10 and 4, you have constants that are variable, h and r. But the setup of the problem is identical, and you treat those constants, limits of integration, whatever they turn out to be, as constants floating through the problem. Your answer is not necessarily numerical, depending on the problem. It might be, in the case of a cone, you might derive the formula for the volume of any right circular cone, which you probably did in Calc 2. So here, I'm not going to do all of these. I have to pull up the problem so I can actually see the wording because I didn't do that ahead of time. But I wrote out the basic setup that we're going to use. So for number 12, find the mass and center of mass of the limb and bounded by the graphs of the equations given below for the given density. Rho equals K. So for this, rho is equal to K. That's my density. And y equals the square root of a squared minus x squared. Y is greater than or equal to 0. Well, I'm sorry, y equals 0 for this. I'm thinking about the actual solution. Okay, so first off, if I want to find the center of mass, as I said in class, those are not formulas you have to memorize. If you ever had to solve a problem like these, you'd be given the formulas. In particular, as I mentioned in class, all the formulas for center of mass and moment of inertia are in your book, listed at the end of the section on double integrals, or it might be technically the section after the section on double integrals in chapter 5, where there are applications. We went over average value of a function and using a double integral to calculate the area under a curve, and then there's center of mass type examples, which we simply didn't do in class. But you have this. The total mass is given by this double integral right here. This is the center around x and y. And then to get the center of mass, you just use that formula right there. One thing to keep in mind, if you're using this, it's m sub y over m, which will give you the center of mass with relation to x, and mx over m, which gives you the center of mass with respect to y. There are reasons for that, which if you think about are pretty clear. I'm not going to explain them here because I'm just trying to solve the problem out. But if you think about that, it actually makes sense. The other thing to actually point out, this function right here is just your density function. Which means in this case, my density function is that right there, rho equals K, or K, which is just a constant, which really just means I'm going to integrate a constant, which will make this pretty straightforward and simple. But now I have this A in here, which is also a constant. But again, I understand all that really means is I am finding the center of mass of every shape that looks like this for every A. And I'm either going to get one solution that would work for every A, or I'll get some formula like the volume of a cone formula that will have an A in it more than likely. And we'll just see as we solve the problem. The algebra, the calculus is always the same. But one thing you can do, as I said in class, if this confuses you, pick a value of A. Just case in point really quickly, let A equal 1. Then you have y equals the square root of 1 squared, which is 1 minus x squared. Square both sides, y squared equals 1 minus x squared. Add the x squared plus y squared equals 1, which is just the unit circle. And now I know that in general, all this is all circles, or in this case, since we want This is the positive, so it's the top half circle in the xy plane, and y equals 0. These are just all half circles centered at the origin above the x-axis, and A is just my radius. So now I know what I'm doing, and again, literally, you can say, okay, that's y equals 0. This is the graph I get if A is equal to 1. This would be the point 1, 0. That would be the point negative 1, 0. Good, now replace 1 with A. That's A 0. That's negative A 0. Nothing changes. But now I know, okay, that's what I'm going to have to deal with. Well, now I'm good to go. One thing, and I have stressed this in class, I don't necessarily care how you solve these. You have to solve them algebraically. But we now have rectangular, polar, cylindrical, spherical coordinates. You can convert back and forth here. Meaning, that might be kind of messy for me. But, well, like, maybe here, if I have to plug the y in and then integrate it, maybe I don't want to have to integrate that right there, or I don't know. So, we're actually going to manipulate this a little bit. We're going to convert to polar. If I convert to polar, well then let's see, what is the region I'm integrating over? My radius, clearly anything enters the graph through 0 and goes out through the top of the half circle. So my radius r just goes from 0 to A. Could be 0 to 1, whatever. My theta is clearly just going to spin around the top half of the axis. So 0 will be less than or equal to theta, will be less than or equal to pi. Now I have limits of integration too. Now I can just set up my integral and be good to go. So first off, let's see. I need to find m first, or at least I'm going to find m first. So m is equal to the double integral over d of sigma xy dA. But now I know I'm going to convert to polar. And let's see, theta is going to go from 0 to pi. R is going to go from 0 to A. Sigma xy, that's just my density function, which is a constant k. But I remember, since I converted from rectangular to polar, I have the conversion factor. It's actually kr dr d theta. Don't forget the r. Now just integrate that really quickly. Let's see, the integral from 0 to pi. With respect to r, that becomes kr squared over 2, evaluated from a to 0, which is the integral 0 to pi. That's a bad a. The 0 won't matter, so that'll be k a squared over 2 d theta. With respect to theta, that whole thing is a constant. So I get k a squared over 2 theta, I drew a sigma, theta, evaluated from pi to 0. Again, the 0 doesn't matter. So I get k a squared pi over 2. And there's my m. So now over here, because I'm going to need all these, I'm going to have to erase k a squared pi all over 2. It's 1/3 of the way done. Now find m sub x, which is by definition double integral d x sigma xy dA. But I just plug in, it's the exact same region, so 0 to pi, 0 to a, x, but I converted to polar. So in terms of polar, and I'm sorry, I'm doing m sub x first. So y, I got the two flipped in my head. Y, in polar, y is r sine theta. So that's r sine theta times my density function, which is k, times my integral, again, conversion factor r, dr d theta. Simplify, rewrite, whatever. 0 to pi, 0 to a of k r squared sine theta dr d theta. Integrate with respect to r. the integral 0 to pi of k, and now I'm going to reorganize this, sine theta r cubed over 3, evaluated from 0 to a, d theta. Again, the 0 doesn't matter, so I get k a cubed over 3 sine theta now integrate with respect to theta. And I get k a cubed over 3, antiderivative of sine is negative cosine theta, evaluated from pi to 0. And now I suppose I have to plug in just to be clear and write it out. So I'll get negative k a cubed over 3. If I plug in pi, I get cosine of pi, which is negative 1, minus, if I plug in 0, cosine of 0, which is 1. Minus 1 is negative 2. There's a negative out in front. So I get 2k a cubed over 3. 2k a cubed over 3. Now, do the exact same thing here. The only difference when I set up my integral, this, instead of being y, will be x, which means here I'll get r cosine theta. I'm going to leave off actually solving that one out. The integration is identical to what we just did. But then ultimately, when I write my center of mass, we have m sub x. So my second coordinate for my center of mass would be m sub x, which is 2k a cubed over 3 over m, which is k a squared pi over 2, and then simplify all of that out. Let's see. This k will cancel that k. The a cubed will cancel the a squared and leave an a right here. I have a 2 here. This 2 will come up top, so it'll be a 4. This a will stay there. This 3 will go to the bottom, and this pi will stay on the bottom. And I think we get 4a over 3 pi, if all my arithmetic and algebra is correct there. But you get the idea. Straightforward and simple. You're given the formula. Plug in the density function. Here, plug in x and y. If you left this in rectangular, those would just be x and y, and you would integrate, no big deal. Since we converted to polar, we had to convert x and y to polar. And again, remember, when converting from rectangular to polar, when you integrate, you have that r dr d theta. And that's also a way for me to remind you that when you convert from rectangular to polar, or rectangular to cylindrical, or rectangular to spherical, you have all those integration factors that kind of pop in. Make sure you're remembering all those when solving these out. And again, I do stress from an exam perspective, because I know that's all you really care about. You need to know how to integrate. You need to know how to graph out your region by hand or in Maple, and a lot of these we've graphed by hand. You need to be able to find the region that you're integrating over and express it. You need to be able to list out with that region your limits of integration, which will then let you set up your integral and then integrate, accounting for integration factors and things like that when you convert to polar, polar, cylindrical, spherical, whatever. Any type of application that requires a special integral type formula, that I'll just give you, because then all I'm testing is your ability to take information that you're given, plug it into the specific formula, and then do the math and solve it out. Because here you just say, oh, this is the thing I'm given, check. D, I have to find my region. When I find my region, that then dictates my limits of integration. The rest of this is straightforward and simple. If there are other questions, let me know and I'll make more videos doing these.